maybe I can do this in half an hour, so we're done at 8.
You won't be kicked out until past. So.
All right. So thanks for hosting this, Holger, Mammar, and others. I really liked your talks, and I'm going to talk a little bit about explainable machine learning with R. This is a topic that I've been sort of fumbling around with for some time and trying to keep up with the literature, which is quite diverse, and there is a lot of terminology and things that haven't settled, so I won't bury too deep into definitions, but more focus on showing some packages and code. My name is Mikael. I have a background in research in computational biology, after which I worked at IBM actually, and then now I work at Peltarion, which is a company that makes a deep learning platform. And we are also hiring, like IBM, so data scientists and machine learning engineers and so on. So if you're interested, you can contact me on those contact details, Twitter or email, or maybe talk to me afterwards. But it might be easier to go through that route. So, right, explainable machine learning, or interpretable machine learning, or algorithmic transparency. There's a lot of related concepts which are sort of overlapping. And why do we even want this? I've had discussions both at work and at Twitter with people who say, well, who cares really? If you got a good accuracy on your validation set, you have a good model, and everything is fine. Like why do you even want to have some kind of explanation? But actually there are a couple of different reasons why you would want that, and I will outline some of them. So one thing is simply debugging your model. Like there is one relatively famous example that I don't recall the exact details of, but someone had made a classification algorithm for medical images which had a really high accuracy. But when they drilled down into what it was actually using to make the prediction, it turns out that it was looking at a kind of stamp or watermark that had been left by a specific type of equipment, which they had in a certain facility to which they sent the more serious cases. So it's actually not learning anything from the medical content of the image, but just some proxy variable of the facility. And on the way here, I came up with another example from my own work where I helped a company that had developed their own classification model that would help them predict an action, like what should we do given these data. And they showed their latest model to me and were really happy, like, yeah, we have really high accuracy. And then I ran some very simple variable importance analysis, and the most important feature that came up that was much more important than the other ones, it was actually a feature that they couldn't change. It was something that was fixed, so it was completely useless for making the decision, because that was a condition that was not changeable. So that's one thing. And then according to GDPR, this always comes up, but one of the things that it says there is that you are entitled to an explanation of why you have been adversely affected by an algorithmic decision, like you didn't get a loan or something. Then you have, in principle, I don't know how much this is done, but in principle you have the right to know why the decision was made in that way. And yeah, this point is kind of related to my first point, but sometimes you can find out that the algorithm is inadvertently discriminating against some group just because of the data that it has seen, and like implicitly discriminates against certain groups. So it's a kind of debugging as well, but more about bias. And then it's kind of also about building confidence in a model. If the end user gets a feeling for what the model is looking at, it's much easier to accept that, okay, this is a good model that I can trust. For instance, I could imagine that if you're a doctor, you would be very dissatisfied with just getting a number from a black box. But what is this based on? You would really like to know that it aligns with your knowledge. And just in general, like working with customer projects, in my experience, the customers are always really happy to see some sort of description of the model. So it's sort of a goodwill thing as well. Right. So there are different kinds of interpretability. This thing can be sliced up in many different ways, I found, but this is my current way of slicing it up. So you can first think about model level interpretability versus prediction level, like understanding the model as a whole somehow, or just one prediction, like why didn't you get the loan? And then in both of those you can divide it into model agnostic or black box and model specific interpretability. So some models are considered to be intrinsically interpretable, like maybe linear regression. You can quite easily read off, like with some caveats, you can sort of read off the coefficients. Decision trees, you can follow the path that you take through the decision tree to arrive at some decision. But usually you get better accuracy if you use like gradient boosting or something like that. So then it's not as interpretable, at least not at first glance. So for the model level part, you can look at which features are the most important overall, various feature important methods. You can also look at how much each feature affects the output on average. And for model-specific model level interpretability, you can try to understand the inner workings of the model. Like in neural networks, you can try to sort of look at different weights and activations and see what patterns you get. But then there's the prediction level, like this single case with a loan, or why was this image classified as a tumor. Then you have black box models that I will come back to a bit, black box explanation models. For instance, surrogate models where you actually use the fact that linear models or decision trees are interpretable and just build them on top of your actual model. And then there is a method based on game theory, which I will talk a little bit about, or at least show some code with the Shapley values. And of course there are model specific ways. I will show, I think, one example of XGBoost where you can try to construct an explanation based on knowing how gradient boosting works. And for neural networks, there are various ways of using how the gradients flow, the derivatives flow through the model. I will not talk so much about that because it becomes very detailed. So I guess I already said that there is a diverse literature and everyone is using kind of different terminology. So here are some examples of things that can be interesting. A new preprint to serve your methods for explaining black box models. The second one is a more GDPR legal paper where there's one computer scientist, one lawyer, and one ethicist who have thought about how to do this in a good way. I'm not going to talk about their approach. It's also a bit different. This "Why Should I Trust You" is, I guess, the first high-profile paper of this kind that introduced the LIME method that I will mention again.